13B, 13C. I'm just finishing off 13B, and then I'm going to do 13C using transformations, what you've learned to apply to 13B and 13C. All right, here we go. First one. So, in the last session, you learned how to do these kind of problems. We learned to use tree diagram or factor tree to break down these into their factors to solve. I showed you how to simplify, making sure the bases are the same. So as long as the bases are the same, you can simplify it. The one thing I haven't shown yet, just in case you get intimidated by a lot of numbers and square roots, is question 3. The idea is very simple, but in terms of looking at it, it looks hard, and it's not meant to be hard. Yeah? Let's do the first one, and then I'll move through B, and you can see the pattern to it, and then I'll do E. Okay, so let's have a look at this one. A. The reason why this one looks hard is because you've got, and I'm going to highlight it for you to see, you have 2x minus 1 multiplied 2, and then suddenly you got a square root of 2x minus 1. The reason why it looks hard is because you got that extra 2x minus 1. If I change this problem, which is what I want you to learn to use because it's got to be useful in year 12, when you get something that looks difficult, but it repeats itself, so 2x minus 1, 2x minus 1. Notice the other ones. X squared minus 1, x squared plus 1, x squared plus 1. Notice this one, x minus 1, x minus 1. This is x minus 1, that's x minus 1. This is 5x squared plus 1, 5x squared plus 1. There's a pattern here. So when you get to year 12, they will often do this where they make it look hard, but it's not. And one of the reasons why is because they're repeating the same factors. So what I want you to do here is to make it easier for yourself. If you notice there's something repeating, okay, let it equal to something simpler. Make it like this. If you said let A equal to 2x minus 1, suddenly question A becomes, instead of bracket 2x minus 1 times root of 2x minus 1, you now have A multiplied to root of A. That's much easier. That's something that you wouldn't have been intimidated. If I gave that as a first question, I said simplify this, you would have been like, oh yeah, I can tackle that. But if I gave you this one to begin with, you'll be like, oh, that looks too difficult, I don't know how to do. But all I've changed is your perception of the problem, okay? So now, if we change this perception to A times root of A, this is easy to do. Because root of A, what is that the same as in terms of power? What is it the power of? A to the power of? A half. When you're talking about root, that was last session, I talked about square roots. It will be root is the same thing as saying to the power of half. Now using your index laws from 13a, if you multiply the bases are the same, what do you do to the powers again? What do you do? How do you multiply? How do you add or multiply? So if I gave you a to the power of 2 times a to the power of 3, what do you do to the powers again? You add them. This one would have been a to the power of 2 plus 3, which is a to the power of 5. Well, it's the same thing with this one. This is a to the power of 1, so it's a to the power of 1 plus half, and 1 plus half is really just 1.5, or 3 over 2. This is your simplified answer is a to the power of 3 on 2. But we know what a is because I just made it up before. I made it up to make it easier. I said let a equal to 2x minus 1. So if you replace a with 2x minus 1, then the answer has to be 2x minus 1 to the power of 3 on 2. That's how easy it is. Okay, and that's why I'm trying to say that the reason why it was hard because you have the 2x minus 1s. And now, the reason why I'm saying that the skill that you want to take is to recognize when it's hard and how do you simplify it. Because I'll show you a year 12 example that my year 12s were asking just before, and I just showed them. This was the problem they had. They had 3 minus k e to the x minus e to the negative x equals 0. Their job is to figure this one out. Now, when you look at that, you're like, no, I've never seen this. This is a quadratic problem. And then when they look at it, they're like, I don't know how to do this, right? But what's repeating there? What do you see that's repeating? E to the x. Okay, anything that's repeating, see if you can replace it. And if you actually try, whoops, if I rewrote this equation, this is 3 minus k e to the x minus, now, remember negative powers, you can rewrite that as 1 over e to the x. True? Because if you have a negative power, you can swap it, and it becomes, say, for example, if you had a to the power of -3, it's the same thing as writing 1 over a3. Okay? So now if you do that, and if I let e to the x, if I take another step and I said, let a equal to e to the x, suddenly your problem changes here. You now have 3 minus ka minus 1 over a equals 0. And remember when I said to you guys from the very day one, I said, if you don't like fractions, what do? How do you get rid of them? How do you cancel it? Yeah. See, if that's divide a, you don't like divide a, you don't like that fraction. Well then if it's opposite of dividing a is times a. Times every single thing by a, and suddenly you get a quadratic equation. Why? If I times this by a, this becomes 3a. Minus, if I times this by a, this becomes ka squared. Minus times this by a, it cancels out, so it's minus 1. And suddenly, you've got a quadratic equation where if you move everything across, it's 0 equals to ka squared minus 3a plus 1. Now surely, this is something easier to work with. If I gave you this from the beginning, you'd be like, oh, feels like quadratic, something similar. But if I gave you that from the beginning, you're like, I have no idea. And what was the skill you're taking out of it? Is that. That's what question 3 is about. Question 3 is about what can you do to simplify the problem of perception. Perception-wise, it's all mental game when it comes to mathematics. We're trying to make it easier to work with. And then from here, we're now using, answer to the question. It was using discriminants to solve it. But that's what my year 12s were doing. And the little step there is understanding how to change the problem to make it easier. Okay, so that's question 3. How do we feel? Pretty good? Easier to do? Yeah? All right. Now, moving on to today's lesson. That's 13b. It's the same problem with e. So if you're going to use the same theory that I just showed you, how do you do e? What's repeating in e? What's repeating? Square root of x minus 1. It's not just x minus 1, it's square root of x minus 1. So if you don't like that, let a equal to square root of x minus 1, and suddenly now you have 1 over a plus a. Surely you can do that. See, that's a fraction. That's a fraction. If you add those two together, it's 1 over a plus a over 1. That can change now to 1 over a plus a squared over a. Is to make the denominator the same, times this by a, times that by a. So you get a squared and a. You can put them all together now. You can write it as 1 plus a squared over a, and you simplified it. Replace a. Put a back in. See, once you simplify it, it makes it easy. You can now replace it back, and you get your answer. See, my answer here, 1 plus square root of x minus 1, but then all squared divided by root of x minus 1. Now the squares and the square roots will cancel out. See, if they cancel out, you're left with 1 plus x minus 1 over root of x minus 1, and you can see the ones cancel out. Your final answer is just x over root x minus 1. But you wouldn't have been able to see that without making it easier. Okay, so I'll move that a bit to the side so you can see. I'll do it again. I'll do it again over here. So I said, in the first step here, I said times this by a, times this by a. I get that. I write it together. It's 1 plus a squared over a. But then if you replace a again, you now have 1 plus square root of x minus 1 squared all over square root of x minus 1. But you already know that the square and the square roots are going to cancel out. So they cancel out. If you square root and square it, they're inverses, so they cancel out. If they cancel out, you only now have 1 plus x minus 1 all over root of x minus 1. And you can see the ones will cancel out. Okay. Yeah, because if you remove the square root and the square, you're only left with an x minus 1. So 1 plus x minus 1 cancels out the 1s, and you get that answer there. Okay, but what have I really shown you in question 3 is this step. Okay, so anytime you see something repeating, it doesn't have to be surds. It can be e to the x, it can be any brackets. You see anything repeating, that's the skill you can take. Make it easier for yourself to solve, and come back to it later. Okay, it's a very essential skill for year 12. That's how the examiners will do it, to try to trick you in year 12. Okay? All right. once you copy that, that's 13B. 13A was revision of index laws, what you've learned from 7 all the way to 10. 13C, which is what we're doing today, transformations, up, down, left, right, thin, wide, reflection. All of that you're going to use on an exponential graph. Okay, so hopefully by now you've learned how to recognize when it goes up, down, left, right, where the negatives go. If you've got that, today's lesson is very quick and easy. Okay?
If Mr. Chairman,
Yep.
if the x is the indices, does that mean the A term also goes?
No. A is just a number.
A is the base. Or
Base number, yep. A will be the base. But X will change.
No, I mean like the term dilating.
Oh! Yeah, we use a different letter for it.
Yeah, so now use A for base.
Yeah.
right.
We use a different letter for it.
So now, so what's the
If
letter?
you go on the indices, you make it like A times 2x and that's
I don't understand what you mean.
like, you know how times something by x?
Yep.
And then that dilates?
Yep.
Does that apply?
Yep. So you would have, let's say, 3 to the, instead of 3 to the power of x now, you would have, let's say, 2 times 3 to the power of x. That's a dilation from the x-axis. Or you can have 3 2x. That means now it's dilation from the y-axis because you're affecting the 2, affecting the x. Yeah. So it's where the x's are. And what you're multiplying to the x's, that's the dilation from the y-axis. Okay? All right. Today's lesson, I want you to copy this down for transformation 13C. Here we go. Exponential graphs is basically now sketching exponential equations. What's an exponential equation, Finn? Shh. Quiet, thank you. An exponential equation is when you have the power of something. So they're saying, what if you had a base 2, hypothetically, it could be base 3 or anything, but to the power of x? What would that graph look like and what are its properties? Kind of like x squared, kind of like square root of x, then this is now 2 to the x. Okay, 2 to the power of x. What does it look like? They all have a property. And your goal is to understand those properties so that you can sketch them. Yeah? Now, let's go with this one. Y equals 2 to the x. You got y equals 3 to the x. You got y equals 3 to the negative 2x. Okay? And you got y equals negative x plus 2. Now, all of these are different transformations. Let's take a step back. I'm just going to have a look at these two. Let's look at the properties. Y equals 2 to the x. Let's draw a table of values so we can picture what it looks like. I'm going to go with, let's say, negative 2, negative 1, 0, 1, 2. Here we go. When x is negative 2, what would y equal to? A quarter. Why is that? Because it's y equals 2 to the power of negative 2. That's the same thing as writing 2 to the power 1 over 2 to the power of 2. That's the same thing as writing 1 over 4. If I sub in negative 1 into the equation, y would now equal to 2 to the power of negative 1, which is the same thing as writing 1 over 2 to the power of 1, which is the same thing as writing half. What happens if I sub 0 in? It now becomes 2 to the power of 0. What's 2 to the power of 0? No. No. 1. Anything to the power of 0 is equal to 1. That's one of the properties, index laws. So the power of 0 is equal to 1. Next one. 2 to the power of 1. What is 2 to the power of 1 equal to? 2. And then finally, last one, 2 to the power of 2. What is that equal to? 4. Now, if we actually plot those coordinates on an x-axis, right? I'm going to go 1, negative, 2, negative 1, negative 2. Let's have a look. When it's 0, when x is 0, I have the value at 1, which is here, 1. When x is 1, y value was at 2, so it's right here. When it's 2, it is now at double the amount, which is 4. Okay, so what you can see is double 1, it gives 2, double 2 gives you 4, so the next one has to be double 4, gives you 8, right? So it's going up exponentially, yeah? Whereas if you look at in the negative direction, I want you to have a look at the negative direction. When it's negative 1, we had half, which is over here. When it's negative 2, we had a quarter, which is half of a half, which is down here. Now, if you join the dots together, we get a pattern here. And I want you to see how the bases change things. When it's 2, on the right-hand side, I was doubling it. Double 1 gives 2, double 2 gives you 4, double 4 gives you 8, double 8 gives you 16. That's called exponential growth, right? But then when I chose negative x values, what was happening instead now? Instead of doubling, I am halving. So I'll be halving it. Instead of half of 1 is half, half of half is a quarter, half of a quarter is 1/8, half of 1/8 is 1 on 16. And it keeps going and it gets smaller and smaller. Now here's the question. What if,
It's a half-life.
yeah, it's asymptotic. Yeah, asymptotic. If I continue to negative 100, it never touches 0. Because it's always going to halve. You're going to always keep making it smaller and smaller, but never can you halve something to equal 0. There is an asymptote. So this graph will keep going. Oh, I've drawn it very badly there. But this graph will keep going, but it has an asymptote at y equals 0. Okay? And then it goes all the way up. And it goes to infinity. Okay, so my range for this graph is never equal to 0, but it will go all the way to positive infinity, and you can never have negative answers. You can never halve something to get you a negative answer. Okay? Half of 1 and you keep halving it.
Maybe we can steal their Wi-Fi.
You can half negative, but that this graph has to be a negative to begin with, which is later on. Okay, so we're now talking about just 2 to the power of x. This is what it looks like. Now there are 2 properties here. Property number 1, asymptote, y equals 0. What's the other thing that we definitely know? What's common? Both of these will have an asymptote. Listening? When it's 3, it would mean tripling on the right-hand side. So you triple it. Then what would you mean on the left-hand side if it's 3? A 30. You're just thirding it. You're making a third, right? So it still approaches 0. But what's common? What else is common between 2 to the power of x and 3 to the power of x? What else is common? There's something about the x though. What else is common? They both have an asymptote and y equals 0. What else do they both have? They would have a positive, yes? But something else. Something else. What is common just on a logical basis? If I asked you to do another table of values for x, y, and there's negative 2, negative 1, 0, 1, 2, what else will be the same? Say it again, someone said it just now. 0. 3 to the power of 0, what's 3 to the power of 0?
1.
1. What's 4 to the power of 0? What's 5 to the power of 0?
2.
The pattern here is an exponential equation. When x is equal to 0, it will always be 1. So if I were to sketch the 3 to the power of x, this is what it will look like. It will be like tripling, so it'll be steeper. It'll grow up faster because it's tripling. But then it'll be a thirding, which is smaller. Okay, a thirding, a half, half and a third. A third would be less, and it'll be like that. Oh, sorry, not like that. Whoops, a thirding. So I have 1/3 down there, and I have halving, which is over here. Okay, so you can see on the right-hand side, I'll be making it steeper, but then on the left-hand side, it'll be flatter. On the left-hand side, when it's negative, it will be flatter. Okay, so if you increase that base to 9 to 10, it gets steeper on one side, and the other side gets really flat. But they both have 2 conditions. Asymptote y equals 0, and they always cross at y equals 1. 0, 1. Those are your 2 properties. Cool? Now, there is one small... Boys, thank you. Listening. One small detail that I normally tell my year 12s, because most people will know the first 2 properties. The third one, students don't normally understand. That's where the year 12 examiners put it in. The third property here is there is a condition on the base value. What can't the base value be? It can't be 0, good. So it can't equal to 0. What else can't it be? 1. Why can't it be 1? Can someone tell me why it can't be 1? Because then everything's 1. 1 to the power of anything is 1. So if you sketch 1 to the power of x is just a straight line. It's just 1. That's not exponential. So it can't be 0. It can't be 1. What about negative? Can I have negative 2 to the power of x?
Yes.
Let's try that. If I have negative 2 to the power of x, so this will now be negative 2 to the power of negative 2. This will now become 1 over negative 2 squared. Now, what's 1 over negative 2 squared? 4. So this is still a quarter. So that's good. I still have a quarter. What about the next one? Negative 2 to the power of negative 1. This is the same thing as writing 1 over negative 2 to the power of 1. This is negative half. Yeah. Now, why is that going to be an issue? Why is it the negative half becomes an issue? Yeah. It's still going to be exponential, but this is what it's going to look like. See, if I sub in 1, it'll be negative 2 to the power of 1, which is negative 2. But if I sub in 2, negative 2 squared gives me 4. So I went from negative 2 to positive 4 to negative 8 to positive 16 and then negative 32. You know, so what will happen is this is what it'll look like. You'll start off with a quarter, but the next one will now be a negative half, which is like down here, negative half. Yeah, and then it will go up, down, but it doubles. The value keeps doubling. It keeps doubling, but yeah, but it'll be positive, negative, but it's not connected though. It's going to be just dots. And so if you type that in your calculator, what happens is it will look like this. It actually looks like a vacuum on that one side. It will look like a vacuum instead of like exponentially out and exponentially in is what it looks like. Okay? So the conditions, the third condition that you have, 1, asymptote at y equals 0. So you're going to asymptote. Condition number 2, you have y-intercept at 0, 1. Third condition is that the base value cannot be less than 1 or equal to 1. Can't be less than or equal to 1. Can't. Okay? Because if you have 1, it's a straight line. If you have 0, it's 0. If you have negatives, it does that effect. So it has to be greater than 1. So it could be 1.2. It could be 1.3. Ah, now this is a good question. Can you have a half? And yes, you can. The reason why you can is because another way of writing half is 2 to the power of negative 1. Now, if it's 2 to the power of negative 1, you can times the powers, and this now becomes 2 power of negative x. Now, using what you learnt from chapter 7, transformations, or even chapter 5 from last term, what happens when I put a negative next to the x again? Anyone remember?
It's a reflection in the y-axis.
Reflection in the y-axis. So, your graph before was an exponential graph that looks like this. If I ask you to reflect in the y-axis, it will now look like that. This is y equals to 2 to the power of x. This is y equals to 2 to the power of negative x. Okay? But then what happens if I put a negative in front of the 2? What if I had y equals to negative of 2 to... Yeah, it'll be upside down, reflection in the x-axis. So now this is what it looks like. Y equals to negative of 2 to the power of x. Notice I'm putting the brackets in so you can see the base is always 2. It's always larger than 1. Base is 2 to the power of x. 2 to the power of x, 2 to the power of negative x. They're all base 2s. Yeah. How would you do it this way now? How would you go this way?
Oh, it's just like
2 negatives. It was just like a square root. It's like a square root function. If you wanted to go this way now, that would have to be y equals negative of 2 to the power of negative x. 2 negatives. Negative on the function, so negative outside the function, and negative on the x, we'll flip it this way. But they all have an asymptote of 0, and they all cross through 1. This is 1 and this is negative 1. Okay? But that's transformations, and we're just doing reflections there. So now you know that, we can do things like adding 1 on, moving up, down, you can move it left, right, and that's what today's exercise is about. Tying in what you've learned in chapter 5, in chapter 7, transformations, to put in an exponential graph. That's how simple it is. Yeah, 5 was like square roots, hyperbolas, truncus, circles. All of that, how you move the up, down, left, right is exactly the same for exponentials. So if you learnt that well, you can do it here too. Okay? All right. So what I want you to copy down were the first 3 conditions. Now this is what I want you to copy next. I want you to copy the transformations. Now the letters could be different in your textbooks, but I want you to copy this one down. Okay, P is your base. Okay, P is the base, and 2 to the power of something. This is what you're adding on. That's when you're multiplying. And I'm going to describe what each one does again. It's exactly the same way as you did quadratics, exactly the same way as you did square roots, exactly the same way as you did for hyperbolas or truncuses. It's all the same. If you add on a value, what does that do again? What does this do again? So if I gave you y equals 2 to the power of x and I added a 1, up and down. It tells you up or down. Add tells you up, minus tells you down. Okay, so this tells you up or down. Add or minus, right? The negatives you knew already. Negative on the outside is reflection of the x-axis. Negative on the x, reflection of the y. So we know that one. What about if I did to the power of x minus 1? What does this do? What if I change? C was minus 1 and B is 1. What happens if I have 2 to the power of x minus 1? What does that do again? If you affect the x's, what are you doing now? What's the x minus 1 do?
Yeah, did this.
No, the up down was the D.
Oh, no, up down right.
Left and right. Okay, it's like your square roots. Remember square root equations, y equals root of x. If I change what I'm affecting the x, if I did x minus 1, that moves left or right. But remember the technique I showed you. How do you know if it moves left or right? What do you do?
Make it equal to 0.
Make it equal to 0. And I explained to you from chapter 7 why we let it equal to 0. It wasn't actually equal to 0. It's actually let it equal to x dash. And then that's or let it equal to x and then solve it. That's what I was doing. Okay, but to make your lives easy at the time, I just said let it equal to 0. Okay? But the reasoning here is if you want to know if you're moving left or right, let this equal to 0. So in this case here, what would you be moving? Where would it be moving?
Right one.
Yeah, right 1. Whoops. Oh, what happened there? This one here would be, if you let x minus 1 equal to 0, x equals 1, this tells me to the right 1. So that's what bx plus c does. Okay? Now, just trying to remember, what happens if I put a 2 in front of the function? So if I said 2 times the square root of x, what does the 2 do again? It's the a value. What does this a do again?
Dilation of the x.
Yes, it's affecting your y values. This is now a stretch. You make it thinner by stretching it from the x-axis. Okay? So here, if you're multiplying this equation by a number, you're now stretching it vertically. So if I gave you an example, it would look something like this. If I gave you 3 times 2 to the power of x, that 3 will stretch it vertically because it's affecting the y values. Okay, because this whole thing is a y. That's the x there, this is the y values. So, that 3 is a stretch vertically. But what do you think the b does? If b is the number of times into the x, if I put a 2 here instead, or 5, what does the 5 do to the x? It's a, what does it do? It is a stretch. It's dilation again, but this is dilation from the y-axis. Okay, and remember, when we're dealing this from chapter 7, if it's a 5, it ends up being like the reverse. Yeah, remember how I told you, if you let this 5x dash equal to x, you'll find that the transformation, this is from chapter 5, if you remember, chapter 7 that we just did our sack on. This tells me that it's 1/5 from the y-axis. So that means you're squishing it in, you're compressing it in instead. Okay, so if you put a 5 here, it's actually compressing. So it's stretching it in rather than stretching it out. If you want to stretch it out, that would have to be like a fraction. So if it was x on 5, you'd be stretching it out that way. Okay, that's the tricky part. Whereas dilation from the x-axis, if that's 3, it'll be 3 this way. Okay, if it's a third, it'll be compressing a third. Okay? But when it's 5 here, it's not 5 that way, it's actually 5 inwards. That's what it is from what we understand. That's your new equation. So 5 times the new, you want to know what the transformation is, divide both sides by 5. That tells me I'm doing 1/5 of the old. 1/5 of the old x. So that means you're shrinking it in. Okay? So now that we've got the transformation, I'm going to do a bit of a GeoGebra so you can see. Yep. P is the base. So 2 to the power of x, 3 to the power of x, yep. So here we go. Let's try
Are you going to use the graphing?
Yep, I'm going to get you guys to see what happens. I think I might have done it here already. Actually, here we go. We've got one here. Once it loads. And remember, the level that I'm teaching you at is much higher than what the textbook will give you. So if you go back to the textbook, you'll find it's very easy to read. I'm just trying to give you a comprehensive understanding of where it comes from. Yeah? So this is it. I'm going to change D. So, wait, this is, here we go. I'm going to put in the blue graph. And I want to keep it, okay. I'm just going to make this larger so you can see. And I'll color code it as well. So let's do blue, text, let's make it large. All right, here we go. This is your equation. So this is your letter D. Okay, so that's moving up or down. So if I press +1, it shifts the graph from asymptote y equals 0. It now shifts up by 1. So the asymptote now is at 1. Okay, so your asymptote, you can move the asymptote as well. So if it started off at 0, like red, and I put a +1, it shifts the whole graph up by 1. Okay, so watch, if I change that +1 to a +2, see, I want you to see, if I change +1 to a +2, can you see how when I get to 2, it will never touch 2, because the asymptote started off at 0, and now I'm saying add 2 to the graph, and it goes up by 2. Yeah? I mentioned before that if you want to move it left or right, and I'll show you. Watch, if I now keep it as 2, sorry, I'll keep it at, where's 2? 2, I can't get to 2, I'm going to go to 3. All right, 3, okay? Now, if I want to move it left or right, remember it was C. So if I change C to, let's say 1, let's say -1. Oh my God, so hard to do there. -1. In C, when it's a minus, it's moving to the right. If I change that minus to -7, listening? If it's a -7, watch, happens when I move it to the negatives, it will move to the right. So if I move it to the negative, so the larger the negative, it's moving to the right. If I move it to the positives, it moves to the left. See, when it's adding, that's what I mean by the transformation. It's the reverse when you're dealing with the x's. Yeah? Now, same thing with dilations. So watch, I'm going to put this back to 0 again so that we don't have a translation. And I'm going to put this back to 0 again too. Where's that 0? 0. Oh, come on. Yeah, there we go. Okay. Now, let's see what happens when I change B. B, which is what you asked, dilation from the y-axis. Watch this. When I change it to 2, see, it's actually not stretching factor of 2 this way. It's in fact halving. Anytime you affect the x values, you are now doing the reverse. Instead of stretching out by a factor of 2, you're halving. So right here, see, that was at 1, 2. Instead of 1, 2, it now halves. It becomes half 2. See, everything gets shorted by half. You squish everything by a factor of half. So if I want to make it stretch out by a factor of 2, I have to change this to a half. If that was to the power of half x over 2, it would change things. So watch. If I change b to 0.5, see how it doubles? So when I change that to 0.5 now, that's x over 2. Watch that. See that point there? That point there is at 1, 2, and now it becomes 2, 2. Because I've doubled this x value, I've doubled it, rather than halving it. Okay, so this is called a dilation or stretch from the y-axis. But when it's a positive value, a whole number, it's actually squishing. When it's a fraction, it goes outwards. Okay, so that's the confusion between the two, and it's mainly because of how we describe the dilation factor. Okay, so this is what I'm trying to say. So I'll try to draw for you. This is what I'm trying to say. When you have y equals to 2 to the power of 2x, this 2 is actually dilation factor half from the y-axis. Whereas if you had y equals to 2 to the power of half of x, this is now dilation of factor 2 from the y-axis. That's what I'm trying to say. Okay, so 1 actually stretches it out. Next one. So that's B. Let's see what we do with A. So if I go back to 1 again, I'm going to just change this back to 1. Watch when I change A. See, A, if I change it to 2, this is different now. This is a dilation from the x-axis. Now this is cool because one thing that you don't see before, you're timesing all the y values now. See, it was from 1, you're doubling it. 2 times whatever the y values are, that's why it's now 0, 2 rather than 0, 1. Okay, because you're multiplying all the y values. Whereas before, have a look when I multiplied b by 2. Look, if I made b 2, say I want you to see at b, when I make it equal to 2, see how different that is? The point doesn't change because you're multiplying the x values. You're not multiplying the y values. So it's still at the same point. Whereas if you change the y values, then it changes the y values here. That's the difference between the two. One is a stretch horizontal and one's a stretch vertical. That's the difference. Okay? All right. That's all the transformations that you need. So if you have a look at the textbook now, I'll show you how easy it is to do. Chapter... What's 13? Now that's probability.
Oh, that's chapter 9.
All right, I'm just going to go back to the PowerPoint. I reckon I had it. Yeah, here we go. I want you to think about how easy it is now to read. Look at these ones here. Okay? Function notation. You have 2 to the power of x. Now what's the minus 3 do? Asymptote. Goes down by 3. Yeah, so asymptote now is at negative 3. What's a 3 in front of it do? Yeah, dilation of factor 3 from the x-axis, so it affects the y values. Okay, so it stretches vertically, it gets thinner. Yeah? What's the, oh, there's no other thing. That's it. I guess there's only 2 transformations. That's what I'm saying. I'm trying to give you a comprehensive understanding, and then when you go back to this, it's much easier. Every one of these are much easier to do. So negative in front of it, reflection the x-axis. Plus 2, up by 2. Left by 2. Okay? There's no left or right now. It's all pretty straightforward. It's just dilation factors. Okay, stretching. So that's doubling. This is a 30 from the y-axis. All of that, that's now 13C. Okay, so I don't need you to do all the questions, but I need you to understand the concepts. So the better you understand it, you don't have to do all this. You can jump to this question, and you'll be able to picture what it looks like. Test on the CAS. Have you predicted right? Have you done the right thing? If you've done the right thing, you've understood 13C. Tick it off. Okay? It's not about doing a lot of work. It's not about working hard. It's about working smart. Learn the theory, understand how to apply, test your understanding with the CAS, and then test out what you understand from the questions. That's how you do well. Okay? It's not about doing all these questions and then go, yes, I've done a lot. It's not about doing a lot. You can do all these exercises, and I promise you, you won't go far. It's about progressing yourself. Okay? It's like, an example would be like gymming. If you're picking up weights and it's a 1 kilo weight and it's very easy for you can do 1,000 of it. But it won't ever compare to if you did 1,000 kilos and 1 rep of that. That will make a difference. So if you want to push yourself, you go from 1 kilo to 5, 5 to 10, 10 to 15, and eventually at some point you find it hardest to lift. That's what progression is. Yeah. Same thing with studying. It's not about doing a lot of work. It's about progressing your level of understanding. Okay, so that's how you improve your understanding of maths. All right, I'll leave it there. But that's 13C, and you got 3 minutes left before the end.